Thank you. So, actually what I would like to show you today is that we had a so-called wireless tutorial. Just a quick survey. How many of you saw or tried the wireless tutorial? Cool. So, that at least will be new. The reason why we did this is that last year we discussed the new wireless architecture in INET, and in the last year a lot of work went into that part of INET. Actually two guys, Levente Mészáros and Benjamin Seregi, who is not here with us, were the main movers and behind this, so credit goes to them about the super infrastructure we have for the wireless part of the INET. So let's start. Actually what we did is that we created a tutorial which covers increasingly more and more complex scenarios. We start with a very simple one, and then we want actually introduce new features just by juggling INET keys in the file. So nothing else, and some tweaking of NED files. And I want to show you how easy it is to configure or replace parts of the new architecture. Okay, let's start. First of all, we have to create a basic NED file. We will use this one along the tutorial, and sometimes we will a little bit extending this. So let's start with the NED file, just go through that. It's just user stuff. I will skip this for the moment, we'll speak about this a bit later. Actually what we have is that two hosts, and they will communicating using UDP. We will program a UDP application into them to transmit packets. And what we have here is that we didn't hard code the type of the, so we didn't use wireless host or standard host. Rather, we went with this like structure, and we use just network node, and we have a host type here, which is by default set to wireless host. That's done because later we will replace, in a later step, we will replace the node. It's a usual problem that, and the new feature in INET 3 that all the standard hosts and routers and everything implements the network, the iNetwork node module interface, so you pretty much can exchange these types during the experimentation. We have also, of course, we have a wireless simulation, so we have a kind of radio medium which actually does the real job, and we can also replace the type. It's just a generic iRadio medium. We have several implementations depending on how complex or how accurate your simulation has to be. And we have the usual IPv4 network configurator. It's just for, you know, the mandatory stuff to have IP addresses and some routing info. Okay, let's go back to the add figure stuff, because this is something new. It's available in OMNeT 5. You know, we discussed also the Canvas API last year, and we have introduced a way to actually put figures into the NED file. We have some basic figures like oval and rectangle and things like that. And you can actually draw background figures in an NED file. Now we have something more complex. We have implemented a gauge in INET. It's also, I mean, this figure. It was basically just for showing that it's really easy to do that. It's a figure which could be defined something like we give it a name and we define the figure here. Actually, the figure has to be registered, just like a module or something like that with a macro, and then OMNeT knows how to instantiate it from an NED file. You can set the position, size, the max value, and so on. You can give a label, and the funny stuff is that actually you can set a module. This is the source of the data itself. As you can see right now, it's host B, so it's the destination host, and UDP So it listens on signals coming from the UDP inside the host B, and the signal name is received packet. So the cache actually will tick and increase every time host B receives a packet. It's a good measure how much actual packet went through the network. So we will see how this changes in the different steps depending on how we configure the wireless medium and the wireless radius. Okay, just go through quickly on the actual configuration of the traffic itself. It's just the user stuff, it has nothing to do with the wireless. We will run the simulation for 25 seconds. We have a single UDP app, you know the usual stuff. We will send 1 kilobyte packets plus the overhead, and with the exponential 10 milliseconds distribution. That means that on average 100 packets will be sent in a second. So what we expect is that during the simulation, if everything, on average, we would receive 2,500 packets. In reality, you will see it's a little bit less because it's a random process, but really that's the whole data amount we want to push. On the other side, we have just a simple NIC. And now we can go right to the wireless configuration, which is right now pretty basic. We have on each host, we have VLAN cards, and we configure the type name of the VLAN interface to ideal wireless NIC. By default, the wireless NIC contains the 8.2.11 implementation, so because that's the mostly used radio interface, but sometimes you are not really interested in the low-level details. For example, if you are testing the routing algorithm, you don't really care, a wireless routing algorithm, for example, an ad hoc one, you don't really care how the low-level wireless stuff works. You just want to have something that if it's in a range, then it can exchange data. If it's out of the range, then it can. You know how many times people have asked on the INET list or the OMNeT list that how should I configure the power to have 200-meter range or something like that. So it's quite hard to figure out that way. So we have something which is called ideal wireless NIT, or you can refer it as a unit disk radio. You know, it's just you have to define a range, and inside the range everything is received 100%. Outside of the range it drops all the packets, it's out of range. So it's a very basic thing. And what we can have also is that we have this ignore interference tag. So we don't even care about packet collisions and things like that right now. This is something like if you have a ideal wireless NIT and also turn off the interference, then you can see this something like each node pair has a different frequency, so they can speak ideally without any collision or whatever. So for some kind of research, this is very useful. The real good thing is that it's very easy to to configure, and it's extremely fast compared to the other implementations, so you gain a lot of speed with this. So for now we ignore the interference, and we can just set the maximum range for 500 meters. Anyway, these nodes have, like, if I remember, they are 400 meters apart. So right now they would be able to communicate with each other. Okay, that's it. And let's see how sorry. Yeah, this way. Now we have the first scenario, and I will just start it. Okay, it's rather slow, so in fast. It's nothing interesting, it's just go through, and the gauge actually counts them. If I set it to express mode, then we will see that at the end it almost transferred the 250 packets. Okay, for the next step, so we have the traffic, we have a baseline, how much packets we could transmit at the maximum. Step 2, we are using wireless, so actually we want to add some animation. So we can set up, so-called, in the radio medium we have a radio visualizer, and we can set that it should display the communication. We can also give an update interval, so when you see the expanding radio communication, you will it will generate a event every 100 nanoseconds. And we want to see also the leaving communication trails, so successful communications should be also shown on the display, and we will see this type of stuff. It's neat and great for presentation, and you can see also that it's actually communicating directly. Okay, for the next step, we will need some additional nodes.
Can I ask a quick question?
Yes?
On the first example, when you had the radio medium, you didn't have the animation.
Yes.
Did it do anything? Did it have to be there?
The medium, yes, it has to be there because it actually coordinates it's not just for the animation, it actually coordinates the whole wireless stuff. It represents the medium itself.
Okay.
It handles the collisions, calculates the distances and things like that. So it's a kind of coordinated stuff.
Okay.
On the next step, we will just extend a bit the NED file. We will add 3 relay nodes, and we will also shorten the communication range. We have this kind of scenario right now. So we have host A and 3 hosts and the B host. And when we start the simulation right now, as you can see, we have decreased the communication range. So it's no surprise that if we start the simulation, you can see that communication is taking part here, but nothing happens here. The reason is obviously that we just put standard hosts over there, and the traffic itself is not routed because by default the hosts do not route. So what we have to do next is we have to set up some static routing, and it's pretty easy. The normal where we just turn on the forwarding in our hosts, and we instruct it's a little bit more tricky, we instruct the configurator itself that all hosts should be given an address on a 10.00 subnet with this net mask, and the routing metric should be error rate, and you should note that the configurator itself can figure out the range of the wireless stuff because it can estimate, or actually right now it knows exactly the range. So it actually can figure out the connectivity graph, and according to that it can configure the routes. So right now, if we start the simulation, they already will contain, I mean, the routing tables, the necessary routing information. So we expect that the route and the communication starts. So on this path, actually the data can flow. And if we let just the simulation run through, then we will see that all packets have arrived, which is pretty strange because there, if you think that almost we set the fault throughput like 1 megabit, the original, and almost all the bandwidth is already used by host A, and at the same time host R1 is also transmitting, so there should be some collisions, and it just doesn't work that two hosts can transmit the same amount of data on an almost saturated transmission channel. If you remember, then we have disabled the interference between the packets, so that's why we can push through all the stuff. So let's model that one too. Okay, we will turn back the interference, or turn off the ignore interference stuff, and we can also specify a so-called max interference range. It's not the transmission range, but an additional range which describes how far the actual transmission disturbs other transmissions. So we set this up to 500. That means that host transmission to host A reaches directly only host R1, but disturbs the reception of the host B because it's above the 500. It's around 5. This is where the 500 range is. So what we expect right now, that it should everything should I mean it should be able to communicate. Sorry, I have to switch and just run in the let it run in the fast mode. No, I don't want to stop that. And what we see is almost nothing fast. 40 packets, that's all. What could happen? Because it's the other end of the problem, that actually nothing went through. The reason is that we are using this IDR radio, and both of the hosts are just meaninglessly transmitting without checking the channel at all, because the IDR radio has an IDR MAC, and an IDR MAC doesn't do anything, so it doesn't control the media at all. So we have to install actually some media control into the host. At this point, it's easier to switch to the normal wireless needs, but we still configure the radio to be IDR radio, so it's still the same unit disk radio. We just, in the wireless NIC, we can set also the MAC type right now, so it's more configurable. Actually, we could build an IDR wireless NIC also from the wireless NIC itself. It's just a shorthand. Okay, we set CSMA as a media control algorithm, and also we request the MAC algorithm to generate acknowledges. Oh. Okay, so at the next step, if we just check this, then you will see that everything goes through. Just in express mode. And as a next step, we will add some mobility to the nodes. I will do it parallel. So we will add some mobility to the nodes. We will move northwards all the three nodes. And what we will see is actually is, okay, right now we see that almost half of the packets get through, which is pretty much okay. Let's see how the movement changes all these things. Let's configure some movement and just do it. Okay, nodes are moving now, and at some point when this gets out of the range, the communication just breaks and we no longer see. This is of course trivially because we have static routings and we don't actually have a route at the second part of the simulation. So what we have to do is right now we add some host type and we change the host to AODV router. So we have an AODV routing algorithm inside the routes, and let's see how this changes the whole thing. The same communication goes, and if everything goes well, then we will see the new routes actually appearing right here. And we have no communication here, and also a bit more packets were transmitted. Of course, between there is some time when there was no route between the two. Okay, the next step actually is just I won't show this probably. It's very easy to install a battery inside the moving nodes. We just set up all the hosts with a radio state-based energy consumer. It listens to radio, the signals coming from the radio, and then actually subtracts from the node's energy. We have to set up the energy storage type. Right now we are using IDL, which is actually an infinite amount of energy. So we can just see in a energy store.energy balance there is a watched variable, and we could just see and watch how the energy is removed from the battery. Okay, and finally I would like to show that we can also set up, we can add some obstacles here. We have added a new module, it's called environment, it's managing all these obstacle stuff. And what you see is that we just set the tracing obstacle, so this is the way how the attenuation is calculated. We have an XML file describing the actual objects here, the positions, shape, and so on. So if we start the simulation, then we will realize that nothing has changed, and those just easily communicate through the wall. And the reason is that we have that simple radio. We have that simple radio, and we have to actually to have better results. To have better results, we actually have to install a new radio, a more precise. We change the radio medium. Right now we have to calculate, we have to do a more precise calculations and switch all the radio types from the ideal radio. You see, we have to give a lot of physical parameters right now. And if we start the step 11 with the enhanced radio, then you will see that the wall will actually break the communication range, and then later when the node comes out from the behind the wall, the communication also occurs. So this is the way how you can change the radio implementations. Later we can add some additional detail, like the propagation computation could be also changed, which also changes the and makes the model more accurate. And at the end, we could even add some antenna to the radio. It's a constant gain, but you can also set up directional antennas and things like that. So it's just basically adding the antenna type, and with the gain, if you can check, this is a screenshot, I've added so much gain that it actually gets through the wall again. So it's a bit, so much gain that it actually gets to the host B2 directly. So it was maybe a little bit more. Okay, that was not all, but what we have right now, some additional steps for the tutorial itself could be, all these things are already implemented in INET, they are just not in the tutorial. So we could add some step for directional antenna, route changes or battery depletion, so real more accurate different, adding radio noise, supporting crosstalk. It's also possible that two nodes are actually transmitting on a nearby frequency. Introduce some short burst noise. We can have a bit precise radio model thanks to Benjamin. It's actually can deal very low level, can handle very low level details from the radio, like error correction and things like that. Forward error correction, scrambling, and so on. And we have also methods how to optimize your simulation, like adding filters to the MAC layer to drop some packets based on some heuristics like distance and things like that. Thank you for your attention, and hope that this gives some hints how to where to look in the INET. And we would love to see some similar tutorials on different parts from the INET, because we think it's immensely useful for new users in the INET. Thank you very much.
I think we have time for one or two short questions, and more questions later in the discussion. So our questions?
Okay, no question.
But I have a question. I'm not that familiar with INET, but in the previous version there was a thing called channel control, and is that gone now? And then
channel control is the same as radio medium.
Okay.
It's just
that's what I was asking.
It's just a stupid name because you know you don't control the channel. You just it's just the representation. It represents the radio medium or the medium itself, because the wireless framework is flexible enough to even model acoustic transmissions. So I would say channel or medium.
Even wired.
Yes.
Okay.
Wired
Yes.
medium.
Yeah, even wired could be.
Okay.
Are there more questions?
Thank you very much.
Okay, so let's thank Rudolf again.